Greetings, students. The last thing we will talk about in Chapter 7 is specific intervals based on a normal population distribution. We talked about two cases for population mean previously. Do you remember what they were? In the first case we discussed, we assumed that the population distribution was normal, and we knew the value of the population standard deviation. We use this example to derive the method for computing confidence intervals. The second case was for a large sample, and we said that as long as the sample size was large, we could assume that the sample mean had an approximately normal distribution, no matter what the actual population distribution was. The third case we will talk about is for a small sample size from a population with a normal distribution. When the sample size is large, the confidence interval for population mean we discussed, case 2, is valid, whatever the nature of the population distribution, because of the central limit theorem. However, if the sample size is small, we can't treat the population distribution as a normal distribution. We can't treat the sample mean as having a normal distribution if the population does not have a normal distribution. So we can't apply the central limit theorem because the sample size is not large enough. Instead, we have to derive a confidence interval that is tailored to that particular population as a distribution. So what we do is we make a specific assumption about the form of the population distribution and then derive a confidence interval tailored to that assumption. So we develop a confidence interval for population mean that is specific to the population distribution, such as confidence interval for the population mean for a population with a gamma distribution, or one for a population with a Weibull distribution, or whatever distribution. Now, what we will talk about now is a confidence interval for when we have a small sample size from a population with a normal distribution. Both the population mean and standard deviation are not known. We will tend to see populations with a normal distribution more than any other type of distribution, so we will focus here on a confidence interval for that situation. This is the third case for confidence intervals for the population mean. If you remember from the last section, we standardize the sample mean so that X has approximately a standard normal distribution and represents the standardized sample mean. Now, when n is small, the sample standard deviation will likely not be close to the population standard deviation. So the variability in Z is from both the sample mean in the numerator and the sample standard deviation in the denominator. And because of this variability, we would expect that the probability distribution of the standardized random variable is going to be more spread out than the standard normal distribution. We now introduce a new family of distributions called t-distributions. When the mean of a random sample of size n from a population distribution with mean mu, we replace random variable z with random variable t. The random variable t is computed as the sample mean minus the mean of the population divided by the sample standard deviation divided by the square root of n. The random variable t has a probability distribution called a t-distribution with n-1 degrees of freedom. Let's start with talking about some properties of t-distributions. Even though we're still talking about the standardized random variable of the sample mean, we refer to this variable here by a capital T to emphasize that it does not have a standard normal distribution when the sample size is small. Remember that a normal distribution is defined by two parameters. They are the mean and standard deviation. Different combinations of these two parameters result in different normal distributions. Bell-shaped curves, but with different width and heights. With a t-distribution, we have a specific value of a parameter called the number of degrees of freedom. This parameter is denoted by the Greek letter nu. Nu represents the degrees of freedom and is always a positive integer. The t-density curve is pretty complicated, and we're not going into much detail here, but we will talk about a few properties of the t-curve that relate to our discussion on confidence intervals. We have t-distributions with 2 degrees of freedom, 3 degrees of freedom, and so on. Here are a few properties of t-distributions. First, t-curves are bell-shaped and always centered at 0. Second, each t-curve is more spread out than the normal curve, and that's because there's more variability with t-distributions. Third, as the degrees of freedom increase, the t-curve becomes less spread out. And fourth, as the degrees of freedom approaches infinity, the t-curve approaches the standard normal curve. Let me show you what it looks like graphically. As nu approaches infinity, there is less variability in the distribution, and the t-curve approaches the normal curve. So what do we mean by degrees of freedom for a t variable? We talked about this in chapter 1. Degrees of freedom refers to the number of freely determined deviations on which the estimated value of the standard deviation in the denominator of t is based. The number of degrees of freedom for the random variable t is n-1, because even though the estimated standard deviation is based on a sample size of n, if we sum up all the deviations, we get 0. We know that only n-1 of these are freely determined. We don't need to know all the deviations, because if we sum them up, we get 0. So we only need 1 less than n. With standard normal distributions, we used z notation to capture tail areas. We need the same type of notation for the t-curve tails. With the z values, we only specified alpha, but with t value, that is not enough. We also need to specify the degrees of freedom. And remember that alpha represents the area under the curve in the tail areas. Notation for the t value includes both alpha, which again is the area under the t curve, and the degrees of freedom. The notation is, as we see here, t alpha nu. This is called a t critical value, and alpha is the area under the density curve to the right of t. So for example, t.056. This is a t critical value that captures an upper tail area of 0.05 under the t curve with 6 degrees of freedom. We have a few more things to talk about with t curves. T curves are symmetric about 0, so a negative t value captures the lower tail area, and the positive t value captures the upper tail area. Table 8.5 gives us the t values for selected combinations of alpha and nu. To find the t value of a combination of alpha and nu, we find the column with a specific alpha value and the row with the degrees of freedom value We will go through an example in class. Let's talk about how the t-value changes depending on the value of alpha and degrees of freedom. When we have a fixed degree of freedom, what do you think happens to the t-value as alpha increases? Alpha decreases. It increases because we move to the right of 0 and the tail area becomes smaller. If we keep alpha fixed, as the degrees of freedom increase, the t-value decreases. And a larger value for degrees of freedom means that the distribution has smaller spread and approaches the normal distribution. So now let's talk about a confidence interval for t, which is a standardized variable that has a t distribution with n-1 degrees of freedom. The area under the t density curve between the plus or minus t critical value is 1 minus alpha. This is the area between the upper and lower tail areas. The difference between this confidence interval for the population mean and the other two confidence intervals for the population mean is that with this third case, we use the t critical values rather than the z critical values because we use the t distribution rather than the normal distribution. And again, why do we use the t distribution? To account for the higher variability because we have a smaller sample. This third case is called the one sample t confidence interval. We manipulate this equation to get a confidence interval. So now the endpoints of the confidence interval for the population mean are computed as the sample mean plus or minus t alpha divided by 2 with n-1 degrees of freedom times s divided by the square root of n. And in some cases, we're interested only in the upper or lower confidence bounds. So we did this with the one-sided confidence levels before. We don't divide alpha by 2. We just use t alpha. And we can compute either the upper or lower confidence intervals. Let's go through an example. This article talks about manufacturing and testing composite beams that have been designed to add value to low-grade sweet gum lumber. We have data on the modulus of rupture. We have 30 observations here. We have a normal probability plot. How do we interpret this? We construct the probability plot on the assumption that the population has a normal distribution. We have a straight line, so that means our assumption about the normal distribution is accurate. What else do we know? We know that the sample mean is 7,203. Sample standard deviation is about 544. Do you think there's a lot of variability in the sample? Sample standard deviation is pretty high. So now we construct a confidence interval for the true average modular of rupture. The sample size is 20, so it is less than the sample size of 40, which would allow us to invoke the central limit theorem. We don't have the population standard deviation, but we have the sample standard deviation. We know the population has a normal distribution. So it seems like this is an application of case 3 for confidence intervals for the population mean, where we use a t distribution rather than the normal distribution to account for variability. Because we're trying to compute the 95% confidence interval, that means alpha is 1 minus 0.95, so it's equal to 0.05. We have to divide alpha by 2. If we're computing a one-sided confidence interval bound Do we divide alpha by 2? No. The other parameter that defines a t-critical value is degrees of freedom, which is computed as a sample size minus 1. So it is 30 minus 1. The t-critical value is then t.02529. We can find the value of the t-critical value from the tables. And now we can compute the confidence interval by substituting the values of the terms. Sample mean plus or minus the t-critical value times population standard deviation divided by the square root of n. The interval we compute is between 7,000 and 7,406, and we estimate that interval with 95% confidence. What do we notice? Even though we have a sample size that's not too small, the interval is still wide. Why is that? It's because there's a lot of variability in the sample. We interpret the confidence interval is that if we use the same formula on sample after sample, in the long run, the actual value of the population mean will be found in 95% of the calculated confidence intervals. The interpretation is not for a particular confidence interval, but interpreted over the long run. And with that, we conclude our discussion of confidence intervals. Thank you for listening.